Hello students, in this video we'll be talking about auxiliary lines. It's a hard word to say. Obviously I just tried to say it and I didn't do very well. But an auxiliary line is a line that you draw within a diagram which is parallel to two pre-existing parallel lines. Here's an example of one right here, and you can see that it splits any angles that are there into two different parts. It doesn't bisect the angle, but it definitely splits it into two different parts. Another example is over here. I'm going to draw one more auxiliary line, and this time for this diagram, I've drawn a line so that it is parallel to each of the lines that are given to me, each of the parallel lines, and it splits this angle W into two different angles. Now you might wonder, why am I doing that? The reason that we split up a diagram like this is because we can now use our concepts of alternate interior angles to find out something about angle W based on the angles that are pre-existing here. I'm going to get more into this later on in the lesson. But let's take a look at the learning target for now. The learning target says that I can use an auxiliary line, a line that I just told you about, to separate angles. That's what we're going to be doing. We're going to be looking at angles that are given to us and trying to take them apart. And then we're going to try to apply the relationships that we learned about last lesson, lesson 1, between these new angles that we made to find their measures. So all we're going to be doing is finding the measures of angles by looking at relationships between them. Speaking of relationships, what is the relationship between the lines on the top, the bottom, and the dotted line? You should be able to know that all of these lines are parallel to each other. And it's important to note that they're parallel to each other. In other words, this dotted line is parallel to this line up here, and it is also parallel to this line down here. Similarly, this line up here is parallel to the line down there. So we've created multiple different pairs of parallel lines. And if we were to, draw a transversal, that transversal would intersect 1, 2, 3 parallel lines and would create a lot of opportunities for us to use those angle relationships we talked about yesterday. Let's do some definitions. All right, two parallel lines are lines with the same slope that never intersect. Here's a diagram. You can see lines CD and line AB are parallel. The way that we can tell that they're parallel is because they have the same slope. Sometimes they are also stylized in the diagram with these arrows that indicate that they run alongside each other but never intersect. And this is the way to write it out in notation. AB is parallel to CD. Those two vertical lines indicate these two lines are parallel. And of course, we want to make sure our notation is correct, so we're using that line notation above AB and CD. Now let's talk about perpendicular. Now you should remember from algebra that perpendicular lines are lines with negative reciprocal slopes. We'll talk more about that in a later lesson. Negative reciprocal just means we flip the slope upside down and take the opposite sign. And they intersect at a right angle. You can see that right angle marker here. In this case, line EF and line GH intersect at this point. We represent that in notation by saying line EF is perpendicular to, it looks like an upside down T, GH. Parallel to vertical lines, perpendicular, an upside down T looking thing. Now, parallel line postulate. The parallel line postulate states that if you have two parallel lines, like these two parallel lines here, you can draw a line, you can actually draw multiple lines between those two lines that is parallel to both of them. So you can see this dotted line is the line that I drew in, and that line is parallel to both this line and this line. It should make sense to you. These two lines go on forever but never intersect. They have the same slope. As long as you draw another line that has an equivalent slope, that line should be parallel to both of the original lines. Auxiliary line is similar in nature. An auxiliary line is very specific in its purpose, though. An auxiliary line is a line added to a diagram that allows a relationship to be used. A lot of the times you see auxiliary lines, they're going to be parallel lines that follow the parallel line postulate. For example, I'm looking at this diagram and I see that this angle here is 50. Sometimes I can use an angle in a diagram to find other angles, but I can't really find that many other angles. I can find this angle over here, which is 130, but I can't find anything about this or this angle out here or this angle. However, if I draw in an auxiliary line, one that looks sort of like this auxiliary line is going to be parallel to the top and bottom lines. And it also allows us to start using some of the angle relationships. For example, I can see that this angle is 50, and now this new angle that I've made is also going to be equal to 50 because of alternate interior angles. Remember, we're trying to identify a relationship that we can use, and alternate interior is one of those relationships. So we can say that this angle is also 50 degrees. That's the power of the auxiliary line. It allows us to make up information, or determine information, I should say, based on information that is already given. Take a look at this model problem. You should see this auxiliary line that is drawn so that it splits an angle into angles A and B. Now it's asking us for the measures of A and B, and what are the justifications? All right, remember that in order to use this auxiliary line, we need to identify a relationship that we can use. And without having this line here, we wouldn't be able to know this. But with this line, I can see that this line and this transversal and this line, both parallel to each other, form what's called that Z shape, or alternate interior angles. And here's my justification. I know that angle A is equal to 37 because of alternate interior angles. I can use a very similar procedure to try to find the measure of angle B. Keep in mind, angle B is going to be in an alternate interior relationship. Oh, I'm using the wrong color here. An alternate interior relationship with 44 degrees. And we're only able to use these alternate interior relationships because we know two things. Thing number one, this line here is a transversal. It intersects two parallel lines. Thing number two, this line, the auxiliary line, is parallel to this line, the pre-existing parallel line. So now I know that angle B is equal to 44 degrees. There's actually one more thing you can find here. It tells us that the auxiliary line splits angle X into angles A and B. So it basically tells us this original angle before there was an auxiliary line here, this angle was called angle X. We can actually figure out the measure of angle X based on the fact that this piece plus this piece equals the whole thing. In other words, the angle addition postulate. Remember that the angle addition postulate says any angle, in this case X, is equal to the sum of its parts. A and B make up angle X. So I substituted in 37 and 44, and I got 81 is equal to X. In other words, I know now that X is equal to 81 degrees. That was the model problem for auxiliary lines. Let's take a look at the check for understanding. Now, I don't want to give it away because we're going to be doing this in class, but I want you to think about this. If I were to take an auxiliary line and draw it here, that means I would have two different ways of getting the pieces of angle that I've just made. Remember, I cut up the angle W into two pieces, not necessarily equal pieces, but I do know that I can find the top piece by doing this theorem. I'm not going to tell you what it is, but you could probably figure it out from the rest of the video. And I can find out this piece of angle W by using the same theorem. And then adding those numbers together should give us the measure of angle W. But I believe I've said too much already. Since we have a bit of time, I do want to go over one more question, and it's question number 5 on the problem set. I'm looking at this problem and I have two parallel lines, and those two parallel lines are intersected by two other lines. I can't call these transversals because they don't intersect two parallel lines, but I can fix that very easily. I'm going to draw an auxiliary line between them, and most of the time you're going to draw these auxiliary lines, they're going to go straight through an intersection like this. Okay? And I'm going to extend that auxiliary line so it goes a little bit farther out like this. Now, I already know that the entire angle here is 67 degrees. Not bad. I also know that what I've just created is a situation in which I have two parallel lines, this line and my dotted line, my auxiliary line, and both of those lines create a bunch of different relationships between the angles in those intersections. For example, this angle here and this angle here are on the top left of each of the intersections. In other words, these two angles are corresponding. I know corresponding angles are congruent to each other. Now I know this angle is 35 degrees, but I don't know this angle. As a matter of fact, most of the time when you draw an auxiliary line, you're going to create two new angles. You want my advice? You're going to name those angles as simply as possible. Name them A and B. Because I know that A and B are some basic old letters, and I can use those pretty easily in terms of variables. So corresponding angles, I'm able to say that angle A is equal to 35 degrees. Right? I also know one other piece of information. I know that angle A and angle B together are going to make up that larger angle that we already know. In other words, angle A and angle B, whatever those two angles happen to be, have to add up to 67. That's the angle addition postulate. Now we're getting somewhere. Now I know that angle B is equal to 32 degrees. Once I have that piece of information, I have one more thing to do. I wanted to find the measure of angle 3. So I'm going to use one more relationship that I know, and it's my old standby. It's that Z theorem, otherwise known as alternate interior angles, which means that angle B and angle 3 are congruent to each other. So hopefully you saw how easy it was to set up these equations by knowing the relationships. First I identified corresponding angles, then I identified the angle addition postulate, and then finally I was able to use alternate interior angles to find what I was looking for. This was the video on auxiliary lines. Good luck studying.